I will just present or will explain you shortly what ESoC is about, so ECMWF Summer of Weather Code, and also what you can expect today. And then we will jump right into the presentation of the projects. So for those who don't know ECMWF Summer of Weather Code, it's an online program, or online coding program, where each summer developers teams work together on a coding project related to climate and meteorology. And so this year in 2020, ESoC is already in its 3rd edition. And it is already it's always a process where the application starts in January. So this year the application also started end of January, and they closed on 22nd of April. And during this time, people or teams could apply to projects who were published on GitHub. And then the final selection of 10 projects this year was done on 1st of May. And since 4th of May, 10 developer teams work on 10 projects related to machine learning, cloud computing, climate and meteorology. And so today's webinar, and also this is actually a series of 2 webinars. So today we will present 5 projects, and next week we will present the other 5 projects. And so today the projects, they have a chance to present what is the project about, and also what they've done already since for the last 2 months. And the full projects and also the full results will be presented on 16th of October during the final ECMWF Summer of Weather Code Day. Due to COVID-19, it is this year also online, but at the same time, it gives an opportunity for many people also to join and to see what the projects and teams have been working on for the 5-month coding period. So before we start, I would like to just give you a short overview of the projects that will be presented today. And so it's in total 5 projects. 4 projects have a focus on machine learning or deep learning. So the projects are related to machine learning applications. And these are the projects DeepChef and Conversational Virtual Assistant for users of ECMWF online products. Then the project exploring of machine learning or deep learning techniques to detect and track tropical cyclones. And the 4th project on machine learning is applying AI capabilities to address operation challenges in ECMWF products team. And the 5th project is related to implement a reproducible workflow for open data related to seasonal forecast data. And this is the project Unseen Open. And so these 5 projects, they will present today the project teams, also what the project is about, and their midterm results so far. Before we start, I would like to invite you to go to slido.com and enter the hashtag ESoC_AMA, because this is a conversation today. So this is your chance also to ask anything about the projects. If you have any questions about ESoC, but also the projects, please feel free to go to slido.com, enter the hashtag ESoC_AMA, and post your question there. We will, depending on time, so each project will have around 10 minutes time to present their work and their project. If there is still time, after the project presentation, we will answer 1 or 2 short questions directly after the presentation. And if there is no time, then we still have, after all the projects have been presented, we still have 10 minutes time where we go through the questions on Slido, and all questions will be replied to. And now I will hand over to the project team of DeepChef, to Sanurag and Roshni, who will present their project DeepChef. The floor is yours.
Let me get started. We are the first team number 2, actually, part of stream 2, which is called the stream on artificial intelligence. And we have been working for the last 2 months on a project for predicting wildfire danger. This project is called DeepChef. And let me get you to the specifics. So before going into what wildfire danger means and how we calculate it, I'll give you a bit of the background on the project and why we decided to work on this. So wildfires are these very large uncontrolled fires that happen in these forest areas, and they burn and spread very rapidly. And this is very dangerous because it causes the loss of so much land and so many homes, so many forests. And this destruction is obviously very harmful to us. But the problem is that the occurrence of wildfires, although natural, has increased steadily over the past couple of years because of the changing climate and how the climate is getting warmer and warmer for the past couple of years. So the reason we started to work on this is because maybe wildfire prediction can be improved. We do have systems that have been developed over the last decades that are able to predict wildfires. But we are working on this to incorporate the latest technology and developments in artificial intelligence, to incorporate these so that we can account for the patterns in weather, and we can find what exactly are the necessary conditions that can cause a wildfire, whether it's the hot temperature, whether it's the dryness, whether it's the amount of fuel in the atmosphere. And being aware of these exact conditions, what their importances are in the causation of a wildfire, can thereby help us better manage and prevent these natural disasters. So moving on to our project, we are trying to predict wildfire danger, measure and predict wildfire danger. And I've put a screenshot on this slide from the European EFIS system. In this system, we have a classification, as you can see at the bottom right corner, going from very low danger to extremely high danger. And it shows you a map of different parts of the world, and it gives you the coordinates of, which locations have the possibility of a high fire. And this is measured using various indexes. Actually, the one that I'm focusing on right now is called FWI. We are also working on some other indices that Anurag will present you in a short while. But starting with the fire weather index, or FWI, this is basically a meteorologically calculated index that's used worldwide in various systems to estimate the danger associated with a particular fire. What this actually means, if I give you a pictorial representation, is here we see a fire where the FWI index is calculated to be the number 15. And according to the system we are using, this is a moderate fire. If the FWI is higher, that means the wildfire is more dangerous. So here we have another image of FWI where the value is 24, and this is classified to be a highly dangerous fire. So it can get worse than this. This is the entire classification range of FWI. Anything below 5.2 is very low, and anything above 50 is extremely high. The weather readings which are taken to calculate the FWI value are these 4 variables. It's very simple, actually, the calculation. It's using air temperature, relative humidity, wind speed, and rainfall. And these are calculated, these are measured at ground to collect these values at a particular location. And at every location, this is collected at a particular time, which is the local noon, when the sun is directly over the head. And then we arrive at the fire weather index, which is the value that we want to know whether how bad the fire is going to be at that location. So now we have systems that use FWI for the prediction of wildfire. And these systems have been developed since the 1970s and are still in use. The one that we've been working on is the FS system, and I showed you a screenshot in the very beginning. The system works very well, and it gives us, it can predict these forest fire indices up to 10 days in advance. But there are certain aspects of the system that can be improved, like being able to predict in every region of the world. I think currently it predicts better in North America or Europe or specific locations, but it doesn't predict equally accurately all over the world. So that is something that we want to improve. And we also want to improve the time scale of prediction, because currently we can predict up to 10 to 15 days ahead, but it would be nice if we can capture the seasonality or the long-term effects of these wildfires, because this is an annual problem in various parts of the world. Next, I think we'll move on to another index similar to the fire danger index. And this will be presented to you by my teammate, Anurag.
Right. So the overview that Roshni gave you that speaks about one particular index, the fire weather index, and largely what that talks about is what is the danger of a fire getting triggered in a particular place given a certain set of weather conditions. And by weather conditions, we mean those 4 variables that she pointed out. Now, GEF or deep GEF, as we are going to build, constitutes more than just the danger of a particular fire getting triggered. It also talks about how deadly or how bad could this fire be, or like how big or how dangerous is it in terms of the energy radiated. So that's where the fire radiative power comes out. So this is more of an actual fire measurement. So this is based on the energy emitted by an ongoing fire through radiative processes. And this gives us an understanding of how massive this fire currently is. So while FWI was talking more about what is the danger of a fire getting triggered based on weather conditions, this particular index or this particular parameter tells us about how bad or how big or how massive is a particular ongoing fire in terms of the energy radiated from this fire. And traditionally, the forecasting model for the fire radiative power involves a persistent scheme. That is, we assume that the FRP for the following day is the same as the FRP for the current day. Now, we can, of course, improve on that. We can model a better system. We can use machine learning to give better predictions. So that's where we also incorporate this as a part of deep GEF. So just for our viewers who are not aware of what is GEF in the first place. So GEF is the global ECMWF fire forecast. And deep GEF is a pun on that, in that we make a deep learning model that hopefully provides better predictions. Okay, so going ahead, this is an overview of the existing FRP. So this is an actual screen capture from 19th of July. You can see there are some parts in Africa, some parts in Latin America, maybe north of Australia, where there are quite big ongoing fires. And this is the energy radiated from these fires and captured by remote sensing. And this can also be, it's not just on a very low resolution global. You can also zoom in quite a bit. As you can see here, we're looking at 0.5 degree grid cells. So this is from back in June 2015. And we again notice different fires taking place. This is largely in the Asia Pacific region. But the idea is that, yeah, we can capture ongoing fires and their energy in quite good detail, but we want to improve the forecasting of this for the upcoming days. Like, so how this will help us is that given an ongoing fire and a current FRP, we would want to know that over the next 5 to 10 days, is this fire going to get even worse? Is it going to get, is it going to come under control? It is good to have that sort of modeling and prediction. So how do we do this? Like, how is it different? So we take a typical machine learning approach. This is something that is probably the underlying framework for most machine learning projects. You have a lot of data. You train it on a machine learning model. We, in this case, use a deep learning convolutional neural network model, a UNet model to be more precise. And once we have trained this model on this data, and we have some pre-labeled outputs. So we use past occurrences. So let's say for the FWI, we have historical FWI values. So that is what we use as our labels or our ground truth. And then over time, as the machine learns, we are able to make better forecasts and better predictions. So this is a very standard machine learning model. We have not, of course, like developed or invented any of this. Our work is more about optimizing this model to suit both the data and the outputs. And that is what we have been doing over the last 2 months. We have already finished the parts of procuring the data with the help of our mentors from ECMWF. These are quite huge data sets, which is, of course, quite an enjoyable and exciting thing to work with, like 800, 900 GB of data, quite an interesting challenge. And once we were done collecting the data and processing it, we moved forward to actually training our model for predicting FWI. And we're currently in the phase where we work on FRP. And going ahead, as Roshni mentioned, we try to increase the global coverage and also the timescale of predictions. Next up, I'll give you a quick overview of how this happens in the machine learning scenario. So on your left, what you see are the input forcings. These are the 4 variables that Roshni talked about: the temperature, the relative humidity, and such. And they are fed into this machine learning model, and which subsequently produces the output FWI values. So this is a unit style architecture. On our GitHub, we have a lot more detailed overview of this particular machine learning model. So I encourage everyone to go to the ESoC GitHub page and go through all the projects, not just our project. Yeah, and right. So I think I was talking about how it is fun and exciting to work with data, but there are also challenges. So in the global scenario, you don't have a lot of wildfires, which is why wildfires make news. Like, we of course have wildfires, but very large and very big wildfires are not that many, or like not as broad as, let's say, a restaurant in your city, which is why you have this small subset on the left, which tells you that most of the data points to small FWI values. So this is not something that would be a challenge typically, but it is a challenge because we would want to predict all ranges of FWI values. So we want our model to be equally good at predicting high dangerous fires as well as low dangerous fires, which is why we use, again, statistical techniques to transform the data and give us a more uniform distribution. And this has been a learning for us during the course of the work, and it has greatly improved our accuracy as well. Now, diving straight into results. So we have an accuracy level for a 10-day prediction that ranges from 79% to 86%. So this is within the boundary of what we initially proposed when we started the challenge, that we'll have sort of 80% prediction accuracy. And we have this right now for the fire weather index over a 10-day period. Now, these predictions that we make, they use 4 previous days input of weather variables. So the 4 variables that Roshni mentioned, we input those variables for the last 4 days. So let's say today is Thursday, I input that for Monday, Tuesday, Wednesday, Thursday, and I get the prediction for the next 10 days. Now, there is a certain, a more nuanced view of this prediction accuracy, let's say. So for higher values of FWI, we see a certain dip in the accuracy. It goes down to around 60 to 50%. Whereas for something between 0 to 70, which is the moderate and the slightly heavy fire region, we have pretty good accuracies that are within the 60 to 80 range. Right. And the next thing that we're also working on is that we're doing case studies. So we're specifically looking at very small regions, like actual burning wildfires in Australia, wildfires in Portugal, wildfires in Latin America, in Central Africa. And we specifically look at how well does our model perform in these small geographic locations. That gives us a better understanding of how and where can we improve things. Now, this is sort of a very pictographic and visual representation of what we're actually doing. So on the left, what you see is the real FWI that has been calculated after taking historical observations. So it is not the prediction, but the actual FWI based on reanalysis data. And on the right is what you see, our prediction from the deep learning model. And I think it looks quite consistent, at least from a very pictorial and color-based representation. There are definitely some inconsistencies, but again, this meets sort of the 80% accuracy criteria that we're trying to reach. Now, going ahead, I think that is sort of largely covers what we are working. And of course, I would again encourage everyone to go to our GitHub page and take a look at the code, download it. You can always play with it. The code is open source. We have notebooks that anybody can use to explore them. And yeah, we are open to questions now.
Thank you, Anurag, and thank you, Roshni. The results are quite impressive. So due to time, I would just go on to the next presentation, but we come back to questions then later during the Q&A session.
Sure.
And then I invite the project team from the virtual assistant, Frank and Michael, to join us, and the floor is yours.
Great, thank you very much. Yes, this was already very interesting. I learned already a lot, and I'm eager to learn more from the other projects also later on. Let me also start the screen, and now you should see the presentation from us. So we are team number 25, and the project, oops. Sorry. The project title is Conversational Virtual Assistant for Users of ECMWF, C3S, CAMS Online Products and Services. It's a little bit long title, but on the other hand, we have 3 very cute avatars. They are our chatbot avatars. They don't represent the final avatars yet, but this is at the moment what we are using for now. You will later on see them in action in the demo section. So a couple of sentences about who we are. So my name is Frank Lieber. Our teammate, my teammate is Michael Kuhn. You see here our email addresses also on the slide in case there are some questions, or you can reach us via the GitHub page also. We are Germans. We are living in Southeast Asia already for more than 15 years now. We are working in Laos, in Thailand, and Cambodia. I'm currently in Thailand, and Michael is in Cambodia. You see here some pictures of basically the places where we live. And we are building environmental data and information systems also for other organizations here. So this is a little bit about us. But very important also, and I would like to say a big thank you already to our mentors who are Anna, Helen, and Michaela, who are really very helpful to us, answering all our questions and providing a lot of good input to us. And what is also important, they have to wake up quite early because of the time difference. We have our 2 weekly meetings, and it starts quite early for them. So a big thank you to them. And yeah, but now let's dive into the project itself. So the goal, what we try to do is we try to create a chatbot for external users of the websites to get the questions they have answered without the need to make additional use of existing support channels. So basically, users should be able to chat with the bots, and then they should find answers via the conversations they have with these bots, and the dedicated support channels, they have hopefully more time to answer more relevant or the most relevant questions So what are the challenges? The challenges, we are talking there are a lot of relevant content sources we are considering. The content varies a lot in complexity, the structure and the format. And then a little bit more related to the challenge also, because some of the sources are in a Confluence, in a wiki style format. There is a lot of text, and then we try to we use natural language understanding, natural language processing, and these are complex topics where we learned a lot, and we are still learning a lot. And then also the chatbot, the conversions itself, they are present also they have special characteristics. They should feel natural. They should have basically a chatbot should have some kind of personality. And so this is also an area where we learn a lot, or we have learned already a lot, and we will definitely still continue learning there. So what are the users? Basically, we try to provide the services for the ECMWF, C3S, and CAMS website. And the challenges here are that the user groups, they differ. They have many different knowledge levels. There are also different user needs. Some users, they have very detailed, more or less also sometimes complicated questions. Others, they just maybe they look for a job, or they look for some news or whatever. So basically, you can come up with endless conversational contexts, which we try to consider, or hopefully train the chatbots that they answer as many of these conversations. So switching over to the solution path, what we are following, it starts basically, we are building a knowledge graph of the relevant content sources. And then in the next step, we will make use of this knowledge graph to train the chatbot, the conversational virtual assistant. The chatbot platform, what we are using it's a cloud-based solution from Google. It's called Dialogflow. There is some inbuilt machine learning in this cloud solution, so we are building on top of that. We also did some machine learning experiments outside of it, but basically Dialogflow will be an important part for us. And that's why you see the 3 different avatars. Is basically we are branding, or this is at the moment our thinking. We have separately branded chatbot integrations. So the 3 different, that's why we have the 3 different colors, similar to the main website colors. And just the general note, we work in an agile and iterative process, delivering quick or often smaller results, and then basically adjusting our flow, because we are learning quite a lot of new stuff along the way. Oops. No, sorry for that. Okay, so the next slide, our solution, this is just another view. Above the avatars, you see different content sources. For example, the Jira service desk, the data catalogs, application catalogs, and all of these different content sources, they feed into the knowledge base, basically the brain of the virtual assistant. On that slide here, you don't have to read it or understand it, basically just a very short snapshot of what we call the knowledge graph. Basically, different objects, you just need to understand basically that there are different objects, they are somehow linked to each other, and we will then later make use of these different objects and linkages to answer questions. For example, one of these circles represents a data set of the C3S service. And then if a user, for example, has a question about a documentation of this data set, we can then follow the linkage of this in this knowledge graph to look up the related documentation, and then basically what are the questions in that documentation, what are the topics, and so on. So this is basically at the moment work in progress. The conversational flow, basically I will skip over this slide because we don't have so much time. It is not so important for now. Some sample user questions, what the bot should be able to answer. You know, it starts with simple questions. For example, how do I change my password? Or some clarifying questions. Why can't I get any data, for example? Or more general questions. How can I access some data? And the important thing is, I mean, these are just a few examples. We have basically hundreds of training sentences later on. And the important thing is that the bot should be able to keep learning. When a user basically not finds something, that over time the answers, they improve. The technologies, I mean, you see basically in GitHub also the source code. That's why only very short time. We use Kotlin, Java, virtual machine programming language, Micronaut, Dialogflow, Elasticsearch, and Neo4j. And just 2 minutes because we are already over time. Just very quickly about a short demo. Here is a sample. Basically, this is not the real site at the moment, but I hope you can see that on the bottom right. You see that small rubber duck icon included, and then when a user, they can click on it, and then it opens like a pop-up on the side. And then, for example, a user can ask how can I access some data? Maybe there's even a spelling mistake, but still the training sentence, it gets triggered, or the intent gets triggered. And then there are some follow-up options. For example, one of the options, I know the dataset name, or search by keyword, show me a list of available datasets. For example, if a user then selects search by keyword, sure, let me know the keyword term. For example, if I then just type in ice, and then you get like a result. At the moment, the display is not properly formatted, but you see some available data set coming from the CDS, from the climate from the data store. And or for example, you can also search for ER4. Then it's basically you will also find something. Just a very short demo here, or show me the latest news, and then you see some news, and then the user can click on a news, and then it will get a link transferred to the dedicated page. So this was just a very short demo. I'm a little bit already over time, I see. So summary, all of the source code available in GitHub. Our emails are here, and if there are any follow-up questions, please feel free to contact us later on, or in the Q&A section later on. So thank you very much.
Thank you, Frank. It's equally impressive. And also thank you for making the time very late in the evening. I saw it's already 7:30 at your end, so thank you. The same here again. If you have questions, please drop them now on Slido. Go to slido.com and enter hashtag ESoC_AMA, and we will go back to the questions once all the teams had a chance to present. So I would now give the floor to Ashwin, who is talking about his project using artificial intelligence to track tropical cyclones. Ashwin, the floor is yours. Thank you.
Okay. Yes. Right. So can you see my slides? Okay.
Yes, we do.
Yeah. Okay. So hello everyone. I'm Ashwin. I'm currently working on this topic of exploration of deep learning techniques for detection and tracking of tropical cyclones. My mentors are Linus Magnusson and Pedro Maciel. We are working quite, we arrange meetings like twice, like monthly, and the collaboration is going on pretty good. So yes, so yeah, so the project idea is to so the tropical cyclones. Tropical cyclones are mainly the complex and the most harmful events that occur on Earth, like the natural disaster. So we need some kind of accurate prediction, which is essential to make reliable warnings. And these cyclones are located and aggregated into subtypes based on their intensity. Here on the right, I have just added one of the different images obtained from the satellites. So here you have this kind of images that I'm working on. And there used to be a case where people had to manually classify these things, like manually detect the cyclones in these images and then see the intensity and then classify them manually. So yes, so the traditional methods used to be this DORAC technique, which was mainly based on the enhanced IR methods and the visibility of the satellite images. So these were mainly dependent on the expertise of the users. This was further improved in this object DORAC technique, where people started using computer vision algorithms, but not mainly data focused. So these algorithms were mainly using techniques from computer vision, but not exactly something in deep learning or machine learning. But still, it was not very useful. There was further advancement, which is advanced DORAC technique. And in that, people started using regression equations, but still there was a 5 to 10% of error in the estimation. So main idea here is to have some, since we have a lot of data, so there is this idea of using this data and the data intensive deep learning techniques. So here we have basically redefined the task as an object detection task. Recently in 2018, Matsuda et al., they performed this task as a classification task, where they actually used, so they basically cropped the image into multiple parts. They created a database of all these images, and they performed a classification task, like classifying this specific 20 images into different subtypes. But here we don't plan to do that. We just want to automate the whole process at once. So what we are trying to do here is basically just provide one single image, like I mentioned in the previous slide. Just provide the one image and just ask the algorithm to detect and classify the cyclones. So yes, so the data that we have a variety of, so the data contains variety of cyclone types. So some of them are really well defined, like 18Ps, 08S, 20Ps, and many more. But there is this issue that there is a huge amount of unnamed ones as well. So these were mainly, so there are many new cyclones being detected, but those are not thoroughly studied, and thus they are called unnamed ones. So this was the issue. Like here first we had like around 45 classes, and it was just not feasible to process them all. So after that, we moved to creation of just 4 major classes, and based on the pressure values. So we have defined them as class 0, 1, 2, and 3 based on the pressure values. So as you can see here, the class 0 is about 1005, then class 1 is 990 to 1005, class 2 is 965 to 990, and class 3 is below 965. Okay, so the data that we have. So we have data from BaseTrack database from the 2016 to 2019. What the data pre-processing that we have done is we have the center coordinates of the tropical cyclones, and we are basically creating bounding box of 20 × 20 pixels around the centers. So in that way, we provide this kind of input to our model, and then we expect the model to learn and classify, like detect these cyclones and classify them into different intensities from the intensities of the 4 classes that I just showed on the previous slide. Yes, so okay, so now, so this task is basically a 2-stage task. So in the first stage, we hope to like detect and classify the cyclones into different categories. So we provide satellite image data as input. We have the annotation information as the centers of the cyclones, which is provided as the labels. We provide this to the RetinaNet architecture or one of the object detection network that we can use. We have some kind of hyperparameter tuning, which is mainly the eternals of the architecture, which you can check on GitHub. So I will not go into the details of this. And then we asked the model to perform a regression and classification at the same time. So we want to detect the cyclone and classify it. So, and then we have some kind of trained model, so which can be used for the later part of the project. So the later part of the project is mainly to use the model as an inference as well. So we provide the satellite image data with a time dimension. So we want to provide it. Okay, so these images are mainly across time. So the cyclones are moving across time into different zones, and which are mainly called basins. You defined the complete map of the world into 4 basins, and the cyclones are moving across these basins. So what we want in stage 2 is to use the model to continuously track and classify the different cyclones. So that's what we hope to do in the stage 2. So yes, so the current status of the project is, so in the proposal, I had mentioned that I'll be using retinite architecture. I started with the retinite architecture, but there were some issues. So like I mentioned, we had a lot of classes, and the data for each class was not too much. Like we had unnamed class 1, unnamed class 2 for say just 10 to 15 samples, but specified ones like SP0, SP3 for many classes. So there was huge data imbalance, and we could not get good results for that. So, and that's why we refined the classes into 4 main classes based on the pressure. And now we have a better way to train and validate the model. We also came across this Detectron2 API, which is provided by Facebook, which is an open source API. So it provides all the state-of-the-art object detection models. So we can, now the idea is to try out the different object detection architectures that are already available and see which one performs best for our use case. Since this is completely application-based one, so currently the idea is to just try out different models and see which one works the best for us. There's also this idea of trying different parameter settings, like I mentioned, we are using the different bounding boxes here, which is of 20 cross 20, but we wanna we are open to like changing the bounding box size and see the results. Also, the satellite images that we're using are mainly of 8 bit per pixel, but so the current idea is that if we take 32 bit per pixel images, then the size of the processing, it's too much. Like the data is heavy, and like to process that data via GPUs, it's not feasible with the current state of GPUs available. So currently we are on the 8 bit per pixel images, but we are trying to process it with like 16 bit per pixel and all. So that's the next step. So currently, like I mentioned, the first stage, like doing it all the classes, it was unsuccessful, and that's why I do not have some kind of results to show here. But yes, so after this, there is also another idea to perform some kind of image regression thing. So what we can do here is to provide the image as well as and label it with the center point coordinate. Instead of a bounding box, we can just provide the center point coordinate, and we make the network to learn the relation between the image features and the center coordinate, so that each time you provide an image and the label of the center coordinate will learn. And then after that, if you provide just an image, it should be able to provide you the coordinates of the center. And after that, with the 20 cross 20 bounding box size, we can just create the bounding box and get the cycle. So till now, this is what we have achieved, and we hope to perform on this. And the idea could be to combine the things like get the bounding box prediction as well and the center point coordinate prediction as well. So I think that could help us more, and we are currently working on that. So that's all from my side. I'm open to any questions, or depends on that here. Thank you.
Thank you, Ashwin. Also a very interesting project. Also due to time constraints, the same here. If you have any questions for Ashwin, then please drop them on Slido, and we will come back to the questions later. So now the next project, I invite Aditya, who will tell us about their projects, how they use artificial intelligence in with operational challenges at ECMWF. So Aditya, the floor is yours. Thank you.
Can you see my screen?
Yes, we do.
Yeah. So Aditya will take over.
Hi all, I'm Aditya.
And this is Aditya.
Yeah, and we're CS undergrads from BITS Pilani. And for ESoC, we'll be building intelligent anomaly detection systems along with our wonderful mentors, Matthew and Peter. So coming onto the main motivation behind the project, why is this even important? So ECMWF's Mars servers handle millions of requests every day and serve several terabytes of data. And given the large scale and distributed nature of these requests, manually monitoring these systems for failure is difficult. And further considering the sheer stream of requests that come in, even a few minutes of downtime can be very expensive. So through this project, we aim to actually explore how we can use machine learning to actually predict and diagnose such events, such as downtimes, which might kind of delay our services. So it is also important to get an idea of the scale of events involved over here. So every day Mars serves at a million or so requests, and a downtime of even a few minutes might lead to thousands of requests going into a backlog, and that might delay downstream tasks for our clients. So we really try to optimize. So we're really trying to optimize on the kind of the bottom line over here. And of course, if successful, then we could apply similar methods to other operational services within ECMWF. So this was kind of a project with a very high impact and, a very kind of a very central to the way ECMWF works. So yeah, so let's just move on to the dataset and let's see what it looks like. So because this is a machine learning problem, we should actually just start with the dataset. And right, so here we have a sample log file from Mars. And as you can see, we have, it contains several fields, which are shown in bold, and the corresponding values for these fields. So for example, this log belongs to 21st May, and it corresponds to a retrieve request from the FTP5 prod database. So you can see we can use all of these fields to actually understand what's happening inside the log. But it is actually very difficult to do a direct analysis from these logs because one, we have a lot of these. So we have around 1.2 to 1.5 million logs like these every day, and each corresponds to one complete request. So like we have a lot of logs, and then we can't actually use these in any meaningful way. So what we did was we took all these logs and we filtered the interesting keywords from these logs, and we aggregated them centrally so that we can use these to model time series of different variables, such as the number of requests sent in unit time, or the data retrieved, or the amount of data delivered. So we kind of, aggregated all of these in a central database kind of, and then we can use these to actually make all a time series. And on those time series, we can actually apply our, the machine learning methods. So over here, we have a sample time series. And what you can see is that after we have done the aggregation, we have a time series for a specific variable. So over here, we have the time series for the retrieved volume versus the time. And right, and this is for the month of May. So right, and just for some information about this, so over here we had about 40 million logs to generate this whole time series, and its resolution is about 4 minutes. So each data point corresponds to logs that were taken across 4 minutes, and we have 11,000 unique data points. So 4 minutes for and about 31 days. So you may also notice that we have some red lines over here in the graph, and these corresponds to times that the Mars server was switched off. So maybe it was experiencing downtimes, it was having a maintenance period, it was having a planned shutdown. We don't actually know what it was, but it was something that had the server shut down. So we have these as labels. And now we can go forward and we can zoom into one specific section of the time series so that we can examine it in more detail. And so here we have zoomed in onto the 30th of April, which seems to have been kind of a rough day for Mars system because you can see we have a lot of issues over here. And in orange, we have those sets of windows that exhibit the anomalous behavior that we are actually trying to detect. So we have two such regions on this day. And the important thing to notice is that the orange regions, which were originally like labeled by us, match the actual downtimes of the Mars server shown in red. So the story that you can kind of pick from here is that we suddenly see a decline in the volume of data being retrieved from the Mars servers. And this continues on for about an hour for the first case. And after which the systems are restarted. So we see the red line over there, which corresponds to a server shutdown. So that most likely means that the systems were restarted to correct the downtimes. And then what we aim to do is we aim to perform near real-time checks for these types of issues to try to predict and detect these types of occurrences. So over here, we took like kind of 1 hour to detect this. We try to we're trying to optimize this. So maybe 5 or 10 minutes, that would be the ideal case for us. And yeah, so moving on to the next slide, like one of the ways we go about detecting anomalies is by creating KPIs, which stand for key performance indicators. And here we have generated a sample KPI, which corresponds to an inversion of the original time series, which we saw earlier. So this is interesting, as we can see that the peaks in this time series, which correspond to declines in the number of bytes retrieved as we're doing an inversion, they align very well with the actual times when we had an anomalous behavior. So it's very easy from this for even a human to understand that, okay, these were the times when you actually had an anomaly. And great. So now I guess like Aditya can go over the various machine learning methods that you tried over the dataset.
Yeah. So now just to start off, so the KPI was a basic example of how you can detect anomalies. So whenever the KPI scores were high, that indicated an anomaly, but that was a trivial one. So now moving on to the machine learning methods that we started. So once we generated the data, we had around 100 time series corresponding to various keywords and filters. So in this case, FDB5 prod was one database. Similarly, we had something for Mars OD and Mars ER and so on. So then we started applying the methods directly. In general, time series anomalies can have two kinds in a broad way: point anomalies and contextual anomalies. Point anomalies are sudden changes, like a sudden drop or rise that differs from the existing pattern, but it lasts for a very short amount of time. Contextual anomalies are shifts over longer time scale. Suppose you're having a possible server slowdown or there's a resource starvation in any particular resource, then your server will slow down over time instead of one particular sample, but it is still an anomaly overall. Since both of these are very different, we need different algorithms to detect them, but we plan to integrate both of these into a final anomaly detection system. So how do the anomaly detection methods themselves work? So there are three general ideas, all based on the fact that an anomalous pattern will be really hard to predict ahead or reconstruct as such. So one way would be to just compare each time series window, every new time series window that comes up, with the window seen previously. So anomalous windows generally have a very large distance or difference from previous time windows. So this works well, especially while detecting contextual anomalies. With a sufficient window size, you can easily see how a contextual anomaly is different from the previous time windows. The next thing we do is we build models that are trained to reconstruct a window based on a general pattern. So these models, so we use both autoencoders and GANs for people who have the knowledge. These models can easily reconstruct data that occurs in a regular pattern or is part of a normal distribution of data, but it cannot do the same for anomalies. The third thing we try is predicting the expected pattern based on previous window information. So in this case, we just forecast what's going to happen for the current duration. And if it does not correspond to what we forecasted, then we can have an idea of how anomalous it is. So for all of these, we both use statistical models and as well as standard machine learning and deep learning models. In deep learning, we stick to mostly LSTMs and combine them with the ideas of VAs and GANs. So why is this a difficult problem? until now, it seems like looking at the KPI that we were able to detect all the anomalies without much trouble. So firstly, the anomaly distributions are very sparse in the existing server log data. For example, we had around 8 to 9 anomalies in the whole month of May, and considering each point that we sampled as anomalous point or not, we had only 1% of the total time series being an anomaly. So learning generalizable concepts or just learning concepts that you can apply later from a small number of points is if you have very little data, is a hard task in ML. Further, several of the points that we see that might seem to be anomalies, maybe a downtrend in the time series, might just have a benign cause, like something like a plant shutdown or a system update. So these things are stuff that we don't want to catch, because creating false alarms will just lead to people having to check again and again. And further, anomalies in the positive direction. So supposing you have the servers performing much better than expected, we don't want to catch those. So reconstruction based models sort of struggle with that a bit. Finally, the log files are generated only after the corresponding requests are completed. This creates a minor issue because when there are ongoing requests, those have the most recent information. So we fail to get the most recent information about the time series. Say the last 5 minutes, we don't have an accurate picture of what's going on. So this makes the real-time setting slightly trickier. So as of now, we've applied several machine learning models and deep learning models, but I won't be able to go into the details due to a lack of time. But here are a few results we have. So this, just going through the methods and the results so far. So this is BANPI. BANPI is a simple algorithm. It's used for change point detection. So it detects whenever a time series deviates from an existing global pattern. As such, it is more useful for detecting longer anomalies of the contextual kind. So in this graph, you can see out of the points that we have labeled, the red lines and the blue lines correspond to the anomalies that we were provided, as well as anomalies we have labeled ourselves. BANPI seems to detect the larger anomalies, say the ones around 21st and 27th and so on, fairly well. You can see a spike in the anomaly scores. But for the smaller anomalies, it has a slightly harder task. So for that, we have one more method known as Luminol. So Luminol is a sliding window similarity based anomaly detection algorithm. So it falls in the paradigm where we take a window and compare it to the previous windows. And it is more suited for detecting short-term anomalies. So here we seem to be catching more of the anomalies between 3rd and 7th. Since time series generally come with inherent noise themselves, none of these methods are a crystal clear predictor, but the idea is through combining these models through an ensemble or through gathering the predictions in sort of a combined way with, say, if conditions or thresholds, we will be able to reduce the false positive rate significantly. Then moving on to Telemanon. Telemanon is a deep learning method that uses time series forecasting. So in this case, it forecasts the window that's going to be the most recent one, and then takes a comparison with what actually happened. And then based on the ratio of what happened, we sort of get an anomaly score. This is more useful in a real-time setting. So when we combine the techniques together, some methods will be more relevant in a real-time setting, but others will also add confidence to our model that this is an anomaly. Finally, moving on to Donut. Donut is based on a LSTM VAE based architecture. So we try to build a reconstruction of every time window, and supposing we're unable to reconstruct a time window well, that indicates that it's been out of distribution and is likely to be an anomaly. So having a look at this in the training set, I mean, the validation test set is a more clear picture. We don't have too many labeled anomaly points, so verification is a bit of a hard task. But so here you can see the anomaly score, the lower the score, the higher the anomaly likelihood. So this is one method that we have. So this is the current progress we have right now. So for further work, we plan to implement and train more machine learning methods, especially on more data. This will help us refine whatever we have and reduce the false positive rate. Even if we're able to say catch half or 2/3 of the anomalies that occur, it will lead to a significant improvement in the system. We aim to adjust the algorithms to focus on negative anomalies, possibly to tuning a loss function and changing thresholds, and to ignore the peaks. So if you were to look at Telemanon seems to have picked up a few peaks as part of its anomaly. Then we plan to combine these into an integrated alarm system. And finally, we plan to package everything into a directly deployable and easy to run format for future use and extensions. So I'd like to say a big thank you to our mentors, Peter and Matthew, as well as Victoria's Manuel and all the people, wonderful people at ECMWF have provided data, continuous guidance, and have kept us going. Thank you. So any questions? I guess depending on the time situation, we can take them up later.
Thank you, Aditya, and thank you, Aditya. Yes, I would say we take up the questions later, but also just knowing the volume of the Mars log files, it's tremendous and amazing what you already did in the project. So quite impressive. Okay. So I would just invite now the final project and presentation today. It's Timo Kelde, who will present the Unseen Open project, which is a reproducible workflow for a seasonal forecasting, data. So Timo, the floor is yours.
Thanks, Julia. Yeah, thanks for making this project available through ESoC and for hosting this event. So yeah, like you introduced, I'm sharing, I'm aware of the time, so I'll try to keep it short and general, but yeah, I'll illustrate what we're doing in this project. So instead of machine learning like we've seen in the previous presentations, here we're looking at creating a workflow to assess extremes beyond the observed record. And let me explain to you first what I mean by this. So Unseen is an acronym that stands for the Unprecedented Simulated Extreme Ensemble. And the idea of this method is that you can simulate many extreme events that could have occurred, but haven't been recorded yet. So therefore, by simulating many extremes, you can better assess what kind of extremes could occur in our present climate. So as illustrated here by the Met Office, you can create many virtual observations and therefore have a larger sample of extreme events that can occur compared to real observations. And the use of this method is that you have a larger sample of extreme events, and therefore you can understand the risk better of extreme events. And through that, you can build climate resilience or, for example, enhance global food security. So this method requires you to handle a lot of data. And thorough evaluation is necessary to evaluate your extreme events that you're simulating. So therefore, we are working on this Unseen Open workflow where you download, evaluate, and illustrate the method. So this can be better taken up by end users. Yeah, the workflow is illustrated here. Everything is in Jupyter, but we do use both Python and R languages. And we've had some discussions about this, but we think Python, XArray, and especially lazy loading of data through Dask is best for data handling and downloading, and extreme value statistics in R is used in the second and third steps of the workflow. Yeah, and if someone has any ideas or thoughts on the workflow or anything else that I present, please ask through Slido or send an email. Happy to get in touch. So I'll quickly take you through a case study that we perform with this workflow, the UK February precipitation. So last February, there was a lot of rainfall over the UK, which caused severe damage. And here in the workflow under downloads, we try to generate this unseen ensemble from the climate data store, the CIS5 dataset in particular. Then we evaluate this data. How robust is the ensemble? Can we use it? And then we illustrate the use of this. So the research question is, with what frequency of occurrence can the extreme event that we have faced be expected to occur, given this large sample of the unseen data set? So then download first. A short introduction to SEAS5. This is the seasonal prediction system of ECMWF. And to calibrate the system, they run the model since 1981 to 2016. They initialize many forecasts. And they initialize it every month. So the graph that's illustrating here shows that the forecasts are initialized every month. That you can pool those months together because they're all forecasting February, and they all have multiple ensemble members. So in total, you have 125 forecasts forecasting each February over those years, which means you multiply your observed record by 125 times. So I illustrate that here on the left in the evaluation step, the time series. So the blue crosses is what we know from the observed record that occurred over the UK. So for each year, we have an observed precipitation average for February. But then within SEAS5, within this unseen ensemble, we have 125 forecasts of what could have occurred. And therefore, in this ensemble, you can find more extremes and find more of the tail of the distribution. Then on the right, so from the time series, you would say that the SEAS5 and EOPS seem similar by eye, but then we propose a fidelity test on the right. I'm not going to go into details here, but that shows that actually there's too little standard deviation, so too little variability within SEAS5. So again, if someone has an idea why this might be caused by SEAS5 or wants to know more about the fidelity test, please get in touch. Illustrating the use. So these is a traditional way to estimate extreme values. So this is an extreme value plot where you, on the x-axis, show the return period. So this is how often you expect an extreme to occur. So for example, and then on the y-axis, the event magnitude. So February average precipitation in this case. And the blue dots are the observed events. So for example, the highest blue dot is the highest event on record that you would expect to occur around once in 100 years within this record of 100 years. And then within the model, within the unseen simulation, SEAS5, you have many more extremes. So therefore you would theoretically be able to estimate what is happening once in 1,000 years. However, this plot also shows the problem here that the black dots do not capture the blue dots. So they do not follow the system because there's too little variability. And therefore it highlights also this importance of evaluation. If you would just use this without thorough evaluation, it could be problematic. And next up, we're thinking of redoing this workflow for Siberian heat wave that we're facing now. So it would be really interesting to see whether SEAS5 and this unseen method can simulate events such as the 2020 event, and then how does this large sample of events compare to the one we're facing now. And in terms of the workflow, this is interesting to test the transferability of our downloading approach, because we're using different variables, space and time scales. And it will be interesting to see whether our evaluation methods are robust as well. Do we encounter other problems? So that's what we're going to work on in the coming months. So then wrap it up with the documentation. Yeah, check out the Jupyter notebooks, GitHub, and in case of any questions, please ask. That's the presentation.
Thank you, Timo. And yes, I would, as Timo said, I would directly go to the questions and answers session. I will just share my screen because we have some questions on Slido. Can I share my screen? Okay. Okay, good. Okay, good. So we have one question which is actually directed to the organizers of this webinar. There's the question if the presentation is going to be available for offline viewing. So there will be a recording. So the session is recorded and we will make the recording available. So, and we will send you the link to the recording after the webinar. And so you can also, listen it at a later stage. Then there is a question for Roshni and Anurag for the DCHEF project. So how easy would it be to adapt your project to, say, flood forecasting?
Right. So for flood forecasting, what we understand, so Roshni had actually previously worked also on not flood forecasting, but prediction of adverse weather conditions. So we were just having a discussion, and what we understand is that the 4 parameters that we use, we would need to use some other parameters as well on the input side to be able to model flood forecasting. But the machine learning architecture that we use, we do believe there have been cases where UNet has been used as a machine learning architecture for flood forecasting. So that aspect of it could possibly be very well adapted for flood forecasting. That probably answers your question, Pedro.
Okay, thank you. There's also another question for you from Frank. So what is the required input data resolution needed for the 4 parameters of the DCHEF algorithm?
Right, so the 4 parameters, we input them at a 9 kilometer resolution. So that's like slightly less than a degree. So yeah.
Okay, and another question from Mohit. So what is the loss matrix used? So using RMSE generally smoothens the field. Thus predicting very high values becomes difficult. Was this observed?
Thanks for the question, Mohit. So predicting high values is sort of one of the challenges that we faced. We did not use RMSE. We used MAE as our loss metric. And from our understanding, the loss metric and the gradients being smoothed was not the challenge. Rather, the data set itself has has a much lower number of occurrences of high FWI values, and that has been the challenge so far. So going ahead, probably as Jeff evolves more and we have a larger data set, once we retrain this model, we'll probably have a higher accuracy even for high FWI values.
Okay, thank you. And then there's now a question for Ashwin. Is the code for the Tropical Cyclones project available?
Okay, so I've currently added the pre-processing scripts, but I'm mainly experimenting with the Jupyter notebooks, so I'll add that soon as well. Yeah.
Okay, perfect. Thank you. So there are no further questions unless now it is your final chance to ask a question on Slido. In the meantime, because we already over time, I would like to thank everyone, especially the speakers today, to present their projects, and it's impressive what you've already accomplished for the last 2 months. I just have 2 remaining slides. As I said at the beginning, this was the first of a webinar series. So the second webinar where we present the other 5 projects of this year from the ECMWF Summer of Weather Code will be next week on 29th of July at the same time. It is 2 p.m. Central European Summer Time. And it will be the 5 projects listed here. So if you go to the website esoc.ecmwf.int, you'll find all the information to the webinars, and you can easily, we ask you also to register for next week's webinar and also hear about the projects next week. So because there were questions already, and also all the projects they set, so ECMWF Summer Feather Code is all about open source code development. And if you go to github.com/ESoC_challenges_2020, you see the projects, and all the projects are also, they have repositories on GitHub, and you can also follow the developments during the coding period. So if you're interested and if you want to get in touch with the project and team members, so please go on GitHub and follow up their work. The same with ESoC, go to the website. As I said, next week we have another webinar. If you're interested in listening into the other 5 projects, go to our website, esoc.ecmwf.int. And you can already save the date. So if you found it interesting today, this was just the midterm presentations. It will be much more interesting and much more impressive even for the final ECMWF Summer Feather Code outcomes. The final ESoC day, it will be online this year, but it will be on the 16th of October 2020. And you will get, so please follow us on Twitter, and so you get all the information on Twitter and also on our website how to register for the final ESoC day. And with this, I thank again all the speakers today. Thank you for your time, for some very early in the morning, for some very late in the evening. And also to all the attendees of the webinar, thanks for joining today. And please also join us next week. And I wish you a nice remaining day or evening, and hope to see and hear you next week. Thank you.